Okay, good morning, everyone, to the Local Agency Traffic Safety Academy. I'm Anthony Schmott from Tyndale Oliver. Quick introduction on the webinar that you're here. Everyone is seeing my screen. You have the invitation that got you to the location. I always like to point out on here, my email address is there if you have any technical difficulties getting to our website and downloading the webinars for the presentation. This webinar is being recorded and will be posted on the website. Our coordinator, Dennis Balloon, his email is here as well. Any questions about the presenters, follow-ups, or upcoming topics, he's the person for that. And most importantly, we also have a link down at the bottom to the Tampa Bay Traffic Safety webpage where the local area Traffic Safety Academy site lives. If you click on that, it takes you to this site here, and it shows you the upcoming webinars that we have scheduled pending for the rest of the year, as well as the completed webinars for 2018. Scrolling further down, it's got some more information, and all of the past webinars and recordings are here for 2018. These are the ones that we've done. I've already posted the PowerPoint for the presentation that's being given today, and it is also in your handout pod for GoToWebinar. Down at the bottom, this is also in your handout pod, that we have the PDH, the Professional Development Hours request forms for any professional engineers that are seeking development hours for that. And Dennis will talk about the credits for the planners. With that, I will hand it over to Dennis for introduction of today's topic and our speaker.
Thank you, Anthony. Good morning, everyone. Let me do something real quick. This is Dennis Falloon. I'm the FDOT Local Agency Traffic Safety Academy Coordinator and Consultant, and I want to welcome you to the 7th webinar for the 2018 FDOT Local Agency Traffic Safety Academy. And today's safety webinar topic is guidance for evaluating the safety impacts of intersection sight distance. And this is going to be presented by Scott Himes, who has a PhD. He's a professional engineer, and he's a highway safety engineer, and he works for Venture One out of Raleigh, North Carolina. And with that, I want to kind of give you an introduction to the Safety Academy, and then I'll reintroduce Scott, and he'll give his presentation. As we said before, this is the FDOT Local Agency Traffic Safety Academy, and it's been put in place for a number of years now to provide information on safety-related issues to enhance your local safety programs. This is the 6th year of it, and we usually have them on Wednesdays, and they usually, the time frame is from 10 a.m. to 12 p.m. There's usually a minimum of 1 hour, but no more than 2 hours. Some topics are more complex, so they take a little bit more time. And these last two items here about registration and on the website, Anthony's already gone over, but just to highlight that. And today, mentioning again, the topic is guidance for evaluating the safety impacts of intersection sight distance. And the next one will be next Wednesday. And then we have another one in September. We'll have other ones that will be scheduled later. And as Anthony mentioned, we do offer AICP credits. And sometimes that takes a little bit of time to get in. So just be patient on that end, because I have to fill out a form and everything. Then we have to get it processed into the system. And as he mentioned, also, you can apply for the PDH credits as a professional engineer. And here's my contact information if you have any questions or any concerns about the Safety Academy. And then also I'd like to just add about Scott, who will be Scott Himes, who will be our presenter today. He is a highway safety engineer with VHB in Raleigh, North Carolina, and he has more than 10 years experience in transportation safety. He's also a graduate from Penn State University. He's got a PhD that he earned in 2013, and he focuses on implementation of advanced safety analysis methods, identification of innovative data sources, and evaluation of safety strategy effectiveness. one of the things I thought was real interesting in his bio, he serves as a critical reviewer for the CMF Clearinghouse. So just so you all know about that. So with that, I'm going to turn it over to Scott.
Thank you very much.
Anthony, give him the screen.
Well, welcome to the presentation. I'm going to be presenting the results of what was the National Cooperative Highway Research Program Project 1759, which was the safety impacts of intersection sight distance. Just to give you a little overview of myself, sometimes it's hard to get a face with a name when you're doing a webinar like this, so I just wanted to let you know who will be talking at you today and provide my contact information here. If you would like to forward me any questions or have any discussion after the webinar today, please feel free to reach out to me. As well as, if you have any questions as they occur to you, please feel free to ask them. I'm pretty informal when it comes to this and always happy for the interruptions because I know I do have a little bit of a monotonous voice, so it's nice to break it up with some questions every now and then, so I'm not just talking at you for the next hour and a half or so. So I wanted to start off with an introduction of the NCHRP 1759 products. The first thing that came out of this is NCHRP Report 875, which is the guidance document itself. It's a pretty short document compared to other NCHRP reports. I believe it's only about 36 pages, and I'm going to be providing an overview of it as part of this presentation, as well as the NCHRP web-only document 228, which is the actual report for this. So the report provides a little bit more detail on background of the literature review we conducted, as well as a review of agency practices, the data collection we went through for getting the intersection sight distance, and then more information on how we developed some crash prediction models and translated those into implementation guidance. Additionally, there is a kind of canned PowerPoint presentation available on the NCHRP website. It provides a little bit more details on the background and methodology. It kind of follows more in line with the report, whereas this presentation today hits the highlights of the report and then focuses more on the guidance and provides more examples here of how to use the results of the research. There were 2 transportation research record articles that came out of this as well. The first article presented some of the interim analyses that we had conducted, but focused mostly on the data collection methodology. And then the second article, which has just come out recently, focuses more on the actual safety impacts of intersection sight distance, which talks in greater detail about the methods I'll be providing here today. And I also wanted to thank and highlight my co-authors on this research. Kimberly Eccles of VHB was the lead on this research, as well as Tim Gates, who was at Wayne State University at the time, now is Michigan State University, and Chris Monsier, who's at Portland State University, which you'll see from the states we collected data. We were pretty strategically located to the states for which we collected intersection sight distance. Providing an overview of the presentation, I'm going to just start with a brief introduction and the objectives of the research, which really the overall objective is to take an intersection such as the one shown here and try to answer the question, how does sight distance at this intersection relate to crash frequency? And I'm going to then first go through some details of their final report, talk a little bit about the previous work we looked at, provide more details on the data collection methodology, and then some background on the analysis, methodology, and development of crash modification factors. And then I'm going to talk a little bit more detail on providing an overview of the guidance document using the implementation charts that we developed, because you'll see that the CMFs are pretty convoluted and scary when you first look at them. But with the implementation charts, they're pretty easy to use to calculate what the change in crash frequency would be from changing sight distance. And then I'm going to go through 4 example applications and different ways that you can use the results of this research to evaluate site distance. So the AASHTO Green Book provides minimum criteria for intersection site distance here. And the criteria are presented for approach and departure triangles as shown here. So on the top of our screen, we have approach site triangles, which typically exist at uncontrolled or yield control intersections. And we have departure site triangles, which are used for minor road stop controlled intersections. And we're looking at clear site triangles to the left and right of the minor road approach. And the intersection site distance is calculated longitudinally along the major road here for vehicle A. And so if there's a horizontal curve present, we're not actually measuring the hypotenuse of this line, but we're measuring this longitudinal distance on the major road itself, which I'll talk about in a little bit greater detail. And the criteria themselves can vary according to the minor road traffic control. So we're going to be focusing on case B, which is the departure triangles shown on the previous screen. And they also differ based on the design speed of the major road in which turning movement is being considered. For example, case B2 in the Green Book, it gives criteria for left turning vehicles from the minor road. The criteria are based on gap acceptance behavior at this point, and so the criteria can change based on whether there are tractor trailers expected to use the roadway, as well as the minor road approach's grade can influence the gap acceptance, for which leads to our criteria. However, leading into this project, we realized that the relationship between intersection site distance and safety is not fully understood. We don't know how the criteria themselves relate to safety. So the objectives of this research were to first identify appropriate definitions in existing methods to measure intersection site distance, and then take that information and really develop a standardized method for measuring ISD. And once we've measured the ISD, we wanted to establish the relationship between ISD and safety, and then take that relationship and develop some practical applications that can help with performance-based design, as well as evaluating the safety effectiveness for roadway safety management practices. And going into this research, we realized that there were some key features of the relationship that would be relevant to designers when considering intersection site distance. We felt like the relationship was going to likely be a nonlinear relationship, which means that the safety benefit of increasing site distance, let's say from 300 to 600 feet, is not necessarily going to be equal to increasing it from 1,000 to 1,300 feet. We're likely to see that the safety benefit should be greater for that 300-foot change when the ISD is shorter. We felt like the impact of intersection site distance is expected to vary with speed, hence why the Green Book criteria vary with speed, and that the impact of intersection site distance should vary with major and minor road traffic volumes. We anticipated that as the volumes increase, the impact of intersection site distance would also increase. Kind of the theory, if we had no vehicles that were going to interact with each other, changing ISD is likely to not really have any impact. So some key terminology going into this: the design intersection site distance is the minimum ISD as identified by the Green Book. You may see existing or available ISD used throughout this presentation. That is the intersection site distance as it's actually measured in the field. And then you'll also see proposed ISD come up, which might be an intersection site distance that's under consideration and expected to result from a change at the intersection environment. And then the major road in this case is going to be an uncontrolled approach at an intersection, which is typically the higher traffic volume. And the minor road approach was defined as the roadway that's stop controlled. The drivers must yield to the approaching vehicles on the major road. Additionally, crash modification factors, just for background, I'm not sure of everybody's background in safety, but a crash modification factor, or CMF, is a relative change in crash frequency for a change in specific geometry or a change in crash frequency for applying a treatment, it's a multiplicative factor. So if we had a historic crash frequency or an expected crash frequency, we could multiply that CMF to determine what the future crash frequency is expected to be. So if a CMF is equal to 1, we're going to say that that change has no impact on crash frequency. It's not going to change. A CMF that's less than 1 is associated with a decrease in crash frequency, and a CMF greater than 1 is associated with an increase in crash frequency. CMFs can be developed by crash type and crash severity. For example, if we're looking at putting in a median barrier, we may see that the CMF for total crashes is greater than 1 because we've now put something in the median that can be struck. We would see that crash frequency would actually increase, but the CMF for fatal and severe injury crashes will likely be less than 1. We're going to see those cross-median crashes reduced, which should reduce the crash severity. So we may see different CMFs for different crash types given the installation of even just one treatment. A CM function, which is what we've developed as part of this research, is a crash modification function, and that just implies that the CMF can change due to other roadway characteristics or features. So in this example provided at the bottom of the screen, the CMF for intersection skew angle actually varies with the skew itself. So the higher the skew angle, the more impact it has on the safety of the intersection itself. Another example is that oftentimes the CMF will vary as part of the traffic volume. So we typically see that when you have higher traffic volumes, the CMF will be impacted by that. So we began this research with a short literature review, and what we really found was that the past research related to intersection sight distance was really inconsistent in the direction and magnitude of safety effects. But the review did provide a direction for our data collection plan and identified a lot of features that we should include as part of our data collection in the study design itself. We wanted to make sure that when we were establishing a relationship for intersection sight distance and safety, that we accounted for all the other features that might be relevant to safety that if we don't collect, might get folded into that impact of intersection sight distance. Also from the literature review, we identified potential countermeasures that are currently being used or could be used by agencies to improve locations that have sight distance concerns. Some of them are related to the sight distance themselves. Some of them might be related to delineation. You'll see that we have a brief list that we've included in the guidance document that I'll talk about later. We also conducted a review of documented intersection sight distance practices. The purpose was really to understand how states and local agencies were defining visual obstructions and how they're collecting ISD measurements in the field. It really helped us to determine what processes and parameters we should be following when we developed our protocols for collecting ISD. And so we looked at readily available policies that were online for different state and local transportation agencies. So here you're on the right-hand side of the screen, you'll see an example from the Bureau of Local Roads and Streets Manual for Illinois Department of Transportation was one that we reviewed. And what we really found was that most reviewed policies did not define specific field procedures for determining the sight distance, whereas others did. So the example on the right-hand side of the screen here from Iowa showed a graphic where an assistant and observer went out in the field and were directed to calculate intersection sight distance together. And most of the reviewed policies did include the AASHTO values, which I'll talk about in just another slide or two, for the driver eye height and object height, although there were a couple of agencies that used a value that was higher than the AASHTO policy, where they looked at 4¼ feet for object height as part of the data collection. And we found that many agencies' policies confirmed acceptance that objects can be located within the sight triangle and not necessarily obstruct the intersection sight distance. With our panel, this was one of the big sources of interest we had at our first panel meeting was trying to determine at what point do we actually cut off our sight distance when we have objects such as small trees in view where you might actually be able to see past it, but it does temporarily block your visual vision of the major road approach. And so what we ultimately decided was that if you could move your head or slightly creep forward to see around the object, then it wouldn't necessarily be the obstruction in the intersection sight distance. So for the data collection itself, we captured the intersection sight distance from what's defined as the decision point. The decision point is the location of the driver's eyes when they pull up and stop on the minor road approach of an intersection. The Green Book definition, which is shown on the screen here, defines the location as 14.5 feet back from the edge of the traveled way on the major road, and on the minor road approach, it's 4 feet over from the center line of the minor road approach. The idea here is that drivers generally stop some distance back from the edge of the traveled way, which I think we defined as about 6 to 6.5 feet, and then the driver's eyes are located about 8 feet back within the vehicle. But we didn't find that there was anything backing this up in the Green Book, kind of how this location was really chosen. So we were also directed as part of this research to, at every location where we observed the intersection sight distance, we also watched several drivers approach the intersection and looked at where they were actually stopping. And we recorded that location as the observed location, and then also measured the intersection sight distance from that location. And what we found was that the Green Book was pretty spot on. At 83% of the approaches where we collected data, the actual point where the driver's eyes were was the 14.5 feet back from the edge of the traveled way. So ultimately, we felt comfortable as part of this research to recommend using the Green Book definition of 14.5 feet for the decision point. Then we also wanted to look at the driver and object height, which, as defined by the Green Book, is 3.5 feet in both cases, or 42 inches. And so we developed a target that can be used to measure the sight distance when one person is walking down the roadway to find the point where the sight distance ends. The bright sign helped us to keep an eye on the targeter, as well as the arrow pointing down to the bottom of the sign provided a really good location to identify exactly where that 42 inches is when they're hundreds of feet or 1,000 feet or more away. And additionally, we were interested in making sure that when we were collecting intersection sight distance, particularly because we had 3 different field collection teams, we did not want the field collector's vision to determine where the potential end of the sight distance was. And so what we ended up doing was we found that we could use a laser rangefinder mounted on top of a monopod that had a scope that gave us a 4-power resolution. And so this kind of took our sighter's vision out of the equation here to determine where the end of the stopping sight distance is. And so we used 2-person field teams, with one person being the targeter, which it's a little hard to see from this graphic, but you can see the targeter further down the roadway here with the sign in the roadway. This would be taken from about the location where the sighter would be standing to actually calculate, or on the decision point itself, to observe the targeter. And they communicated with the 2-way radios to tell the targeter when to stop and where they could measure the intersection sight distance. Additionally, we used a maximum sight distance of 1,320 feet, which is 1/4 of a mile, suggesting that really anything beyond 1/4 of a mile is not likely to help in any way. And so in some cases, the ISD may actually be a mile or more, and we felt like it wasn't really worth the effort and time to send the person all the way to the edge of the sight distance to calculate. So we actually cut it off at 1/4 mile. And you can also kind of see, going through our pictures, that throughout the data collection period in the North Carolina sun, our targeter was an intern who lost about 30 pounds from running back and forth collecting the ISD all summer. So our two-person team, the citer and the targeter, used the data collection approach as shown here. So the first step in the approach was for the targeter to move from the decision point down the edge of the traveled way, or if we were in an urban environment, they were able to use a sidewalk to begin to look for the end of the sight distance. And then, depending on whether it was a horizontal curve or the roadway were a straight tangent, would determine how we would measure the sight distance. But the next key step was to determine when the targeter has reached the end of the sight distance. And so the targeter would go to the center of the travel lane and place the target, and the citer would communicate to tell them when to stop and to take the measurement. And once they found the location where the target began to disappear from the view of the citer, if it was a horizontal curve, the sight distance was measured while the targeter was returning using a measuring wheel, as shown on the right-hand side of the screen. And if it were a tangent, then the citer was able to use the laser rangefinder to find a close approximation of the sight distance, which then determined the existing or available intersection sight distance for that intersection. So once we had determined the intersection sight distance, we then had to associate that sight distance with crashes and other features as part of our analysis database. So what we ultimately ended up deciding for this research was that intersection sight distance is associated with a certain target crash type. And we defined our target crashes as all crashes involving a vehicle from the minor road and a vehicle from the major road. We looked at total target crashes as well as fatal and injury target crashes. And so our analysis unit for this was not at the intersection level or even the intersection approach level. Our analysis focused on each of the individual sight distances that we collected. And so the example on the right-hand side of the screen here shows that at any given intersection approach, we had two analysis units. We had the left direction as well as the right direction. And what we did was we associated the features for the left direction with that left direction sight distance, and any crashes that occurred involving a vehicle from the minor road approach as well as from the left direction on the intersection approach on the major road was associated with that sight distance that was collected. So our analysis unit in this case is directional and not aggregated at the intersection level. When I talk about the implementation here in a few more slides, there is a method here for estimating what the crash modification factor or safety impact would be at the intersection level if you were interested, rather than just at the approach level. So we also collected other data, and I'm defining here the relevant data were the data elements that we collected that were found to be significantly associated with target crashes. And so we accounted for those in the model by including the major road traffic volume, the minor road traffic volume, the intersection sight distance that was available. Then we also had collected data in urban and rural areas, so we found area type to be significantly associated, as well as the number of lanes on the major road, the median width, the posted speed limit, the major road shoulder width. And then we also had looked at the major road grade, 100 feet, 250 feet, and 500 feet prior to the intersection. And we found that the major road grade 500 feet before the intersection was also associated with target crash frequency, as well as the intersection angle. We looked at some other data elements that we did not find to be significant within the models. Those included the visibility of the traffic control device. What we were really looking for was for vehicles that were approaching the intersection on the minor road approach, whether they could actually see the stop sign for a significant distance, or if they could not see it before needing to stop. And what we really found was there were no real visual obstructions for the stop sign, so there wasn't really enough data there to look at any potential visibility issues. And then we also looked at the major road lane width, if there was any lighting present at the intersections, the functional classes of the roadway, access density within about 250 feet of the intersection, and then also another measure that we had been considering as part of this research, which is the quality of the sight distance. So the quality of the sight distance, we had worked with the panel to look at objective and subjective measures to define what might be a good sight distance quality. And when I talk about quality, we talk about the fact that independent of the length of the sight distance, it can be difficult to determine how far a vehicle away is and how fast that vehicle is traveling when you're looking down the major road leg at the intersection while stopped on the minor road approach. And so the panel felt that one potential way to look at this is to use objects in the background to help you gauge what the distance is to the vehicle and how fast it's traveling. And so we had initially looked at an objective measure which quantified how many objects were in that sight triangle on the far side or near side that would help you to gauge whether or not you could see that vehicle's distance. But ultimately, we decided to look at a more subjective measure rating from 1 to 3, where 1 is a low sight distance quality, which an example is provided here where there's really just no object to tell you how far away a vehicle is or how fast it might be moving, versus a 3, which in this case, you can see that there are telephone poles that are evenly spaced, as well as trees and other objects that may help you to gauge the distance to that vehicle when you're trying to perform your gap acceptance maneuver. So the initial analysis indicated that having more objects was associated with fewer target crashes, so that kind of sight distance quality 3 did seem to help to reduce target crashes, but it really didn't account for any impacts to single vehicle or runoff road crashes because we didn't measure it. It's more likely that having those objects there was just going to be counterintuitive to safety just in general. And so we felt like it wasn't good to include it, so we did not proceed further with it in the analysis. So for our data collection, we had 3 states, which were all highway safety information states, HSIS. So the crash data and roadway data were readily available from Federal Highway, and also the proximity to our location teams, because we were located in Michigan, Oregon, and North Carolina. We had really good access to the states to go ahead and collect the field ISDs for those HSIS states. So in total, we had traveled to more than 600 intersections and calculated the available intersection sight distance for 1,658 intersection approaches. The sites visited are shown on the map here, so you can see that we looked at kind of central and northwestern Ohio, pretty much across the state in North Carolina, because we do have a lot of varying topography within North Carolina. You can see that we were in the Sand Hills kind of flat area of the state. Then we have the Piedmont in the middle, which is a more rolling terrain, and then a very mountainous section in the western part of the state where we collected data. And then in Washington, we also looked at sites across the state with varying topographies. So in total, for the number of approaches, just to give you an idea, it wasn't really just specific to any facility type or area type. We had a really good mix of rural and urban sites. We had about 400 sites that were on 2-lane roads, and then a really good strong sample of about 400 sites on 4-lane roads, split between whether the major road was divided or undivided. So in total, we had a little bit over 800 approaches that we got the sight distance for, and then we used 4 years of crash data for our modeling. Initially, we wanted to look at 3 years. We were trying to keep the time period a little bit shorter because the sight distance in a lot of cases can really change over time. As foliage grows and trees get larger, it can change the sight distance. So we tried to minimize the impacts of that kind of growth by using 3 years of data, but we found that the crash samples were pretty low. So we had actually expanded the data collection to include more sites to help bolster that, as well as we decided to go ahead and collect an additional year's worth of data because we were looking at a specific crash type, and we did not target the intersections based on safety history. So there were lots of intersections where no crashes had occurred. And so in total, our sample had 726 target crashes included in it. So for our analysis methodology, I just wanted to highlight that we used the kind of traditional state of the practice. We used cross-sectional negative binomial regression, and we really tried to pay attention to a lot of potential biases that can enter in our analysis. We paid a lot of attention to the functional form of the variables that went into our model. We looked at the major road and minor road traffic volume separately, as well as the total entering traffic volume. We accounted for state-to-state differences by including indicators for each of the states. And then we paid attention to correlation among the independent variables. For example, traffic volume and number of lanes tends to be highly correlated with each other. So we made sure that if we included both of those in a model, they weren't highly correlated with each other, which can impact the results. And then overfitting the prediction model. We did only have 726 crashes, so we needed to really pay attention to where we had small crash sample sizes as part of our analysis. So you'll see in just another couple of slides that we had to look at ranges of traffic volumes for our analysis rather than including it as a continuous variable to ensure that we were capturing all of the range and not missing ranges of ADTs when we're trying to implement the results. So low sample mean talked about increasing the sample size in both the number of years we collected as well as the number of sites. And then we also paid attention to potential endogenous independent variables, which is really just another word for site selection bias. For example, we did look at the presence of turn lanes, but we noted that turn lanes tend to be put in for reasons that involve safety. And because we weren't specifically looking at them and we had a smaller sample of sites that had turn lanes, we ended up not having them in the models. But preliminary analyses were indicating that the presence of turn lanes were associated with more crashes, which has been shown in the past to happen because they're put in because of crash frequency. And then we also looked at an omitted variable bias by trying to determine everything we could ahead of time that might be related to intersection safety and capturing those variables in the analysis to make sure the impact of intersection sight distance is truly indicative of ISD and not other missing variables. So we included traffic volume as a categorized variable for interaction terms. Again, we did it because it reduced the sample size. So if we had ADT from 100 vehicles a day on the major road to 30,000, if we included that in the model, when you're trying to go through and then use the results of the model, there may be areas where we had very low sample sizes and the results may not make as much sense. And so to reduce those kinds of issues, we did decide to go with 3 categories, which were traffic volumes less than 5,000, 5,000 to 15,000, and then greater than 15,000. And those categories also help with the ease of application. So we were trying to determine a way to make practical charts to implement rather than using the equations that were developed as part of this research. And we found that by categorizing the traffic volumes, it made the use of the charts a lot easier than trying to interpolate between values, particularly because they are curved. So also for the target fatal and injury crashes, because we had lower sample sizes, we combined the lower and medium categories. So for target fatal and injury crashes, the traffic volumes were greater than 15,000 or less than 15,000. So to capture the potential effects that I talked about early on that might be relevant to designers, we use interaction terms in the models. So any variables that were interacted with intersection sight distance were found to change based on those features. So we looked at the speed limit and what impact it has on intersection sight distance and safety, and then the major and minor road traffic volumes. And then we also found that there were other operational and geometric characteristics that are associated with higher crash frequency, but really weren't found to change the effect of intersection sight distance and safety. So the number of legs was found to impact safety, but it's not really, we didn't find a difference in the impacts of ISD, whether it was a 3-leg or a 4-leg intersection, whether it was the left direction or right direction that you were looking in. But we did find that the left direction was associated with more target crashes than the right direction. And then also the vertical grade. So from our results, the safety effect or the crash modification factor can be calculated by taking the crash modification factor for the condition of interest, which might be the proposed condition or the existing condition, and dividing one by the other. So we can develop a CMF for a new proposed ISD and then compare that to what it is for the existing condition to find out what the CMF is for changing it. And so you'll see from our modeling results, because the interaction terms that we included, the CMF for target crashes, if you wanted to look at changing from a proposed to an existing condition, the equation looks a little bit convoluted and can be a little bit difficult to use. So this is why we were trying to develop practical charts. And in this case, if we wanted to compare to a relative base condition, we chose the quarter-mile distance, which was the maximum value of ISD that we collected as a base condition for safety here. And then we had a similar equation for target fatal and injury crashes, but you can see that there's one less indicator here because we only included high and low ADT. Additionally, in cases where the traffic volume is unknown, we did develop reduced versions of the CM functions that can be applied. And so in this case, you can use the CMF to estimate what the change in crashes would be from the proposed to existing conditions independent of traffic volume. But if traffic volumes are known, the CM functions presented previously would be more reliable and accurate. So having completed the research, I'm going to now talk about the guidance for evaluating the safety impacts, or NCHRP Report 875. So the purpose of this report is to serve as a resource for evaluating intersection safety, and the audience is pretty broad. It's for any practitioners in planning, design, operations, or traffic safety management of stop-controlled intersections that are interested in what the safety effects of ISD are. And the scope for this document is for 3- and 4-leg intersections, for intersections that have stop control on the minor road approaches, and it can be used for planned or existing conditions or planned or existing intersections. So the organization, there are 6 chapters to this guidebook. The first is just an introduction, which does talk about the purpose, scope, and how to use the guidance, and then provides an overview of definitions and acronyms used throughout the research and throughout the guidance. And then chapter 2 briefly focuses on measuring sight distance and other critical information. So it talks about the data collection approach that we used and how to collect intersection sight distance, and then how to calculate or determine traffic volumes if they're unknown, as well as how to identify target crashes and get them from historic crash data. Chapter 3 focuses on the safety performance of intersection sight distance, which I'm going to talk about in more detail here because this is the practical applications are provided in this chapter. So the steps in this chapter are determining the crash modification factor, and then there are also sections here for analyzing more than one approach and then analyzing total crashes. So if we wanted to look at one approach direction that we got ISD for and calculate a total crashes CMF or a total intersection CMF, the steps are provided here to do that. So the CMFs that I showed you a few slides ago were translated into 12 practical charts. The charts are separated by the target crash type. So there are 6 charts for target crashes and 6 for target fatal and injury crashes. And then they vary by posted speed limit. So the charts are applicable for 35 to 60 mile per hour posted speed limits on the major road approaches. The ADT on the charts are treated as group data as they were included in the model, and they cannot really be refined. You really can't interpolate between the curves on this chart. And the charts can be used to evaluate the expected change in crash frequency for changing ISD for either an approach direction, both directions of an approach, or for all approach directions at the intersection level. And so you can evaluate safety effects of changing the ISD at existing intersections or changes during planning and design. So this slide provides an overview of what the charts look like. I'm going to go through more details on how you'll select between the two, but you'll see the left-hand chart for total target crashes has 3 curves on it based on the major ADT. So the light blue curve focuses on major roads that have less than 5,000 vehicles per day. The darker blue is for ADTs between 5 and 15,000. And then the major roads greater than 15,000 is the darkest line. And you'll see that what the models really indicate here is that for higher traffic volumes, changing the sight distance has a greater impact. And you'll see at the bottom right-hand side of the screen, the value of 1,320 feet is the cutoff, and the CMF in that case is 1 for all of those. And then on the right-hand side of the screen, you'll see that we only have 2 lines. That's for less than 15,000 or greater than 15,000 vehicles per day. What we really found was we know that lower volume roadways probably will have some impact from ISD, but because of the lack of vehicles, there was also a lack of crashes for low volume roadways. So we either could not determine the safety impact specifically for very low volume roads, or there really just is no specific impact because the volumes are low and therefore the probability of 2 conflicting vehicles is very low. So there are 5 steps to determining the CMF from the charts. The first step is to identify the minor road approach sight distance, whether it's left looking or right looking, for which you're proposing a new intersection sight distance. So you'd measure the sight distance along the major road for that direction, and that would be labeled as the existing ISD for that approach in direction. Step 2 is to identify the type of crash of interest for the analysis. So you'd be looking at the target crashes chart or the target fatal and injury crashes charts. The third step is to identify the appropriate chart type based on the type of crash and the major road posted speed. So again, you can look from 35 to 60 miles per hour. In this case, we'd be interested in a 55 mile per hour posted roadway. The fourth step is to identify the curve that corresponds with the appropriate major road ADT range. So based on the ADT of your roadway, you would select one of the 3 curves in this case, or 2 curves for target fatal and injury crashes. And finally, the 5th step is then to use the curve to plot the existing and proposed ISD. If any of the intersection sight distance exceeds 1,320 feet, you would just use 1,320 feet and the CMF would be 1. And in this case, if we wanted to compare 2 relative changes to ISD, we could look at the CMF for the major road ADT being greater than 15,000. If the existing is 600 feet, you'd see the CMF is about 1.45. And if you wanted to propose a new ISD that were greater than 1,320 feet, let's say if we removed a sign from the roadside in this case, that we would get a longer sight distance that's more than a quarter mile. We could compare that to the CMF of 1. And so we would take the CMF of 1 and divide it by the existing, which is 1.45, to get our new CMF that would be the reduction. And I have some examples here to illustrate that approach. Additionally, you'll see on the charts that the curves cut off at different values for the minimum sight distance. What we found was that there were small sample size issues, and so for any cases where we did not have data that were less than that sight distance, we did not extend the chart. So when we had target crashes with a posted speed limit of 35 miles per hour, we did not have any sites that had less than 150 feet of intersection sight distance. If I go back a slide, you'll see for 55 miles per hour, we did not have any sites that had less than 350 feet of sight distance. So it's not too common to go out onto high-speed roadways and find very, very small ISDs. We did see that relative to the design sight distance, we had some that were deficient, but we didn't have any that were just ridiculously deficient. So we cut off the curves where we did not have any data to support the analysis further. So moving into chapter 4, this is where we have some example applications. The applications that are listed in there, and I'll go through now, are first for a one-direction ISD upgrade. So if we have just one approach in one direction of an intersection that we want to upgrade the ISD, how would you calculate the safety effectiveness? The second is calculating an intersection level CMF for target crashes. So if we were only looking at one or two approaches, approach directions that we wanted to upgrade the sight distance, what would the impact be overall for the intersection? And then our third example looks at an intersection level CMF for total crashes. So if we know that we can only calculate the effect on target crashes, what is the impact to total crashes at the intersection? And then our last example is a design deviation, just calculating what the CMF would be if we can't meet the minimum criteria in a certain case for intersection sight distance. So for our first example here, for a one-direction intersection sight distance upgrade, we have a three-leg intersection with stop control on the minor road approach, and it has the following characteristics. We're interested in target crashes. The major road volume is 7,000 vehicles per day. The major road posted speed is 55 miles per hour. The existing approach direction ISD of interest is 400 feet, and we're proposing to make a change. We're going to remove a couple of trees here that would increase the sight distance to 750 feet. And so we can look at our practical chart here that we've determined the existing is 400 feet. The CMF is for target crashes. The posted speed limit is 55 miles per hour. Our ADT was 7,000 vehicles per day, so we're going to use the darker blue line that's in the middle. And we're going to compare the existing, which is a 400-foot sight distance, which gives us a CMF of 1.46, to the increased sight distance, which is 750 feet, which gives us a CMF of 1.13. So taking the new CMF divided by the old CMF, that tells us that changing the sight distance at this approach direction from 400 to 750 feet will reduce target crashes by 23%, or gives us a CMF of 0.77. So the resulting CMF is 0.77. It applies to multi-vehicle crashes involving vehicles from the minor road. Because this was left-looking only, it only applies to vehicles approaching from the left. So our takeaway is that increasing left-looking ISD from 400 to 750 feet would reduce target crashes on the approach direction by 23% at this intersection. For our second example, we can calculate the intersection level CMF for total crashes. So for this one, we have a 4-leg intersection that has stop control on the minor road approach, and it has the following characteristics. Again, we're looking at target crashes. The major road ADT is 20,000 vehicles per day. The major road posted speed limit is 40 miles per hour. And we're interested in updating or upgrading the northbound approaches, ISDs. So for the northbound left-looking ISD, we have 250 feet, and we're proposing to get it to 600 feet. For the right-looking, we have 300 feet, and we're proposing to get the sight distance to 600 feet. And you'll see on the right-hand side of the screen here that we have a collision diagram that provides an overview of our target crashes that have occurred at the intersection. So you can see in this period, we have 4 target crashes that involve a vehicle from the northbound approach and a vehicle coming from the left. And we have 5 target crashes involving a northbound approach vehicle and a vehicle from the right. And we have 1 target crash that involves a southbound approach with a vehicle approaching from the right. So again, we can look at our available intersection sight distance. So we've been given we're 250 and 300 feet. We're going to improve those to 600 feet. The CMF is for target crashes. The posted speed limit is 40 miles per hour. Our major road ADT was 20,000 vehicles per day. So we're going to use the darkest line on this screen. And you'll see that improving the sight distance from 250 to 600 feet results in a CMF of 0.51 for target crashes, and the CMF for increasing from 300 to 600 feet is 0.62. So to calculate an intersection level CMF, we can take the CMF multiplied by the number of target crashes for each of the approach directions and divide them by the sum of all the target crashes for the intersection, which is shown on this slide. So again, we had 4 crashes for the left-looking northbound approach. The CMF was 0.51. For the right-looking direction, we got a CMF of 0.62 and had 5 crashes. And then we're going to substitute a CMF of 1 in for the southbound approaches because we're not changing anything. And we only had 1 crash that occurred on the southbound approaches. So including those and then dividing by the total number of target crashes, you'll see that for the entire intersection, our CMF is 0.61 for target crashes. And this applies to multi-vehicle crashes involving a vehicle from the minor road, and it applies to the entire intersection. So we could say that increasing the northbound intersection sight distance for both sight lines to 600 feet would reduce target crashes at the intersection by 39%. So our third example would be taking the intersection level CMF for total crashes. So it results in using similar information, but we need to know the total number of crashes that occurred at the intersection. So our example here, we have a 4-leg intersection with stop control on the minor road approaches. The major road ADT is 17,500 vehicles per day. We're looking at target crashes. The major road posted speed is 60 miles per hour. And in this case, we're going to remove an object in each of the ISD approaches that'll increase it beyond 1,320 feet. So we're going to use the maximum value in this case. And our beginning ISDs are left looking at 525 feet and right looking at 610 feet. So for 3 years of crash data, our southbound left looking direction, we had 5 target crashes. Right looking, we had 7 target crashes. Overall for the intersection, we had 16 target crashes. And we know that the proportion of target crashes to total crashes is 55%. So first we can go to our charts. We identify that we had the 525 and 610 feet of sight distance. We're improving those to 1,320. The CMF is for target crashes. It's cut off here, but this does apply to a 60 mile per hour posted speed limit. The ADT is more than 15,000, so we'd use the dark line on top. And we can calculate the CMFs for our two approaches that we are updating. So for our left-looking approach of 525 feet, upgrading it to 1,320 feet gives us a CMF of 0.61. And for our right-looking, updating from 610 feet to 1,320 gives us a CMF of 0.68. So we can calculate the CMF for the total intersection for target crashes using the methodology we used before. So while we had the CMFs of 0.61 and 0.68, we have a CMF of 1 for the other two approach directions, which gives us an overall target crash CMF of 0.74. And then we can convert that to total crashes using the equation shown, where we take the CMF for just target crashes, -1, and then multiply that by the proportion of crashes that are target, and then add that to 1. So what we find is that for total crashes at the intersection level, the CMF would be 0.86 in this case. So we can say that increasing the southbound intersection sight distance for both sight lines would reduce target crashes at the intersection by 26% and total crashes by 14%. And then finally, in our fourth example, we can look at a design deviation, and in this case, I'm going to use the equations just to show how they are used similar to the charts. You could use the chart in this case, or you could use the equations for any of the other examples that I've shown. So in this case, we have a three-leg intersection that has stop control on the minor road approach, and it has the characteristics that we're looking at target, fatal, and injury crashes. The major road ADT is 1,200 vehicles per day. The posted speed is 50 miles per hour. Our right-looking available sight distance is currently 465 feet, but according to the Green Book, the right-looking design intersection sight distance should be 555 feet. So we're interested in finding out what the safety impacts of not meeting the criteria are. So we can plug the values into the equation. Here we substituted 50 miles per hour in for the posted speed limit. And at the top of our equation, we've taken the existing conditions, which is 465 feet. And at the bottom, we've looked at the proposed conditions, which in this case is the design condition, which is 555 feet. And you can see that by not meeting the criteria, we get a CMF of 1.06. So the existing intersection sight distance for this sight line is expected to increase target fatal and injury crashes by 6% over the design criteria for that sight line's ISD. And then moving on in the guidance document, the fifth chapter in the document focuses on other considerations and resources. This chapter provides countermeasures related to intersection sight distance. However, ISD is just one consideration for intersection enhancement. There are other effective countermeasures available to practitioners. The countermeasures for ISD can be categorized with other measures that improve intersection safety and should be considered in a comprehensive approach to intersection safety. So countermeasures that are listed in the chapter include clearing sight triangles as much as possible without geometric improvements, or doing geometric improvements to improve the ISD. And then we have a category here for increasing awareness and visibility of the intersection. So there could be enhanced delineation leading up to the intersection, larger regulatory and warning signs at the intersection itself, adding splitter islands on the minor road approaches, adding intersection lighting, or adding overhead flashing beacons. Additionally, you could provide warning to the drivers of the presence of conflicting vehicles. So that's looking at intersection conflict warning systems, where you could tell the driver that there's a approaching or conflicting vehicle when flashing. Then we also have choosing the appropriate traffic control listed here. So if there is a safety history a history of crash problems at the intersection, if it is a minor road stop-controlled intersection, you could look at converting it to an all-way stop control, or if warranted, installing a traffic signal or roundabout, as well as a countermeasure would include better accommodation for pedestrians and bicyclists. And then the final chapter is included just to provide the base equations for your reference in the guidance document. So in conclusion, the target crash frequencies do increase as available intersection sight distance increases. As expected, the relationship was found to be nonlinear, and the sensitivity of the number of target crashes to changes in ISD is highest when intersection sight distance is shorter, and that sensitivity decreases as intersection sight distance increases, which just shows that it flattens out as the intersection sight distance increases. The results suggest that the impacts of intersection sight distance on crash frequencies vary as a function of the major road ADT and the posted speed limit. We looked at the minor road ADT, but did not find it to vary in this case with ISD. And I did want to highlight that the research focused on a random cross-section of intersections, and this was done independently of crash history. The CMFs in this case are going to probably be somewhat smaller than if you develop CMFs for before-after conditions for intersections that have received intersection sight distance, because it's just impractical to go and find those currently. But it would be good in the future to do a before-after study to validate this research, as well as look at the potential impacts on intersections that have had a history of target crash issues. With that, I don't think I've had any questions during the discussion so far, but I can take any questions at this point.
Hey, Scott, this is Anthony. Yeah, we'll give folks a few minutes to gather up their thoughts and see if we have any questions coming in the chat. Yeah, it's interesting to hear some of the information about how those crash modification factor formulas and, you know, the empirical calculation of them. I find that interesting because, I mean, we use them all the time. I wonder if, I mean, somewhat related but unrelated, you know, just in CMFs in general, I wonder if you can talk a little bit about the approach or what to do if there's conflicting information in the CMFs. I haven't looked specifically at the information for the sight distance triangles, but I find at times when looking at CMFs that the wording is slightly different depending on the study, and there are sometimes, you know, there's varying degrees of improvement that can be implemented depending on the area. And, you know, if you kind of have any experience or advice for our audience as far as which CMF they should use. I know that's, you know, something that's always challenging when developing, you know, benefit costs and things of that nature, is picking the right one. So kind of like a general CMF conversation.
Yeah, absolutely. So I think the classic example I like to use, if you go into the CMF clearinghouse, there's probably somewhere in the neighborhood of 600 to 700 CMFs for installing shoulder rumble strips. And so, you know, the obvious first case to do is to try and whittle it down to be the most specific you can for the conditions you're looking at. You know, looking at the posted speed, the area type, the number of lanes on the road. And then a lot of times you'll find some comments that some CMFs may be specific to curves. So if you're looking at a treatment that may be specific to a curve, if you can whittle that down to find curve-related CMFs rather than just a general CMF, that would be better. But what you can really start to get into is looking at the quality of the CMF. They may be of different qualities. Before-after CMFs tend to be a little more highly rated, unless it's just a naive before-after analysis. And then you can also look at some of the other information that's available on what was used to develop the CMF. So if you have multiple CMFs that could be applied. You could look at any that are specific to your state or states that are similar to yours for where it was developed. If the data used to develop it were most similar to your situation, some may be more broadly developed, an ADT of 500 to 100,000 vehicles per day, where others may be more specific to 10,000 to 20,000 vehicles per day. And just kind of trying to find those pieces of information, whether you have to go to the original research or not, to look at kind of the conditions that most match what you're trying to do. If that makes sense.
Are you aware of any efforts to, I mean, that was a great example that you gave with the rumble strips. The other one that comes to mind is that we come across is the bike lanes. I forget the exact numbers, but it's something like installing bike lanes is a negative crash reduction factor, and providing bike lanes is a positive crash reduction factor. So, I mean, now you're talking about what's the difference between installing and providing. But with the example that you gave with the rumble strips and there being 600 CMFs, are there any efforts to clean that up? I know that you have the star rating, which helps out, in picking ones that are perhaps better. That's a good starting point, but it's overwhelming sometimes when you search for something and there's 600 CMFs. I mean, are we working on taking the empirical data and the studies and then kind of combining them and getting an aggregate number so that we drop it down from 600?
So that's a really good question. NCHRP Project 1772 is focused on trying to figure out what to do with Part D of the Highway Safety Manual, which currently houses the HSM recommended CMFs. And so I think what you're going to see is the Part D of the HSM kind of move more toward how to use and handle CMFs with more guidance and not recommend CMFs in the HSM itself. And so as part of that effort, I know they're looking at using the CMF clearinghouse to potentially rate and sort of give a seal of approval for the HSM using more criteria than what's used for the star rating. And so you will see some whittling down for the HSM approval that's based on kind of more criteria looking at the reliability of the CMFs that were developed. But I think there are some ongoing efforts as part of that research to look at some of those CMFs that are out there, to start doing some kind of meta-analysis, like you're saying, to combine them, as well as if we have a lot of information on one treatment that has a lot of different effects, we can start to look at the data that were used to develop them to say maybe we're seeing some of these differences because of traffic volume or other characteristics, and start developing more CM functions from the CMFs that are provided to whittle that down and give us better information.
Yeah, I think that's going to be a great effort. It will be beneficial to all the safety, professionals out there, because it's a fantastic tool. But I mean, it gets a little bit tricky. We've had a few questions that have come in to the folks that said, hey, are you guys aware that you're live? Yes, we go live on purpose about 10 minutes before we begin. Let everyone that's logging in know that we're actually here and that you've made it to the right place. And we kind of do a little bit of chatting prior to beginning. Target frequencies, the question specific to your webinar. So target frequencies increase with an increase in sight distance is the question mark. Is that a correct statement? As crash frequencies increase, the increase with an increase in sight distance?
Trying to make sure I word this correctly. I guess no. What we found was that the target crash frequency increases with less sight distance, but I think what's probably being confused here is we're finding so you can see on the graphic provided here that the slope is steepest when the sight distance is shorter. So what we're really seeing is that target crash frequency is higher for lower sight distance. And when you have shorter sight distances, the effects are larger. But as you get out into longer sight distances, those curves flatten out. And so there's less benefit to improving sight distance when you're going from 1,000 to 1,200 feet, and you might get more benefit by moving from 500 to 600 feet because that slope is steeper, so we're getting more impact. But we did find that target crash frequencies are higher for shorter sight distances.
Roundabouts. This research.
Sorry, can you say that again?
Roundabouts. Are roundabouts considered at all any of his research?
No, I don't think any of the sites in this research were roundabouts.
Okay. Someone says, I may have missed this. Are the 12 practical charts included in the NCHRP 875?
Yes, they are all included in the guidance document 875. And they're all in chapter 3. I felt like it wasn't worthwhile to go through each of them individually, but all 12 charts are in the guidance document.
There's a comment that the same person that asked about roundabouts kind of asked about pedestrians, and you know, that's an interesting one as well. When you're talking about sight distances, your pedestrians and your cyclists, this is all taken into consideration as well.
That's another really good question too, and I think I mentioned at the beginning of the call, I kind of came into this a little bit late. The data collection had already happened when I came into this research, so I can't speak to what the panel thought or any discussions that had gone on earlier, but I know that we did not target pedestrians or bicyclists as part of this research.
Okay. I'm not seeing anything else coming in the chat at the moment. I don't know if you have any, you know, sort of final closing statements, words of wisdom, you know, using crash modification factors. I know that before we started the webinar, I was talking to you a little bit about some of the challenges that I've come across. You know, when someone's out there doing a road safety audit and you're looking at the sight distance, you'd like to make some changes, and you know, the obstruction it's inside of private property, or you know, that you have some landscaping, and there's just so many factors that are out there. You know, any words of wisdom with regards to actually implementing some of the quiz. We can do the formulas, we can do the calculations, we can see that it's better, but you know, what challenges people are coming across and ways to overcome that.
Yeah, I guess for me, definitely using this as part of the roadway safety management process, and using these results in a benefit cost analysis could be really useful, particularly, you know, I never really got into, in my examples, exactly what we were doing to improve sight distance, and noting that this is only specific to target crashes, and in a lot of cases, while you have a CMF of 0.5, you may be working from a pretty low baseline. You know, if there are 4 target crashes that you're really getting at. So using this methodology to help with benefit cost analysis will really help to determine if it is worthwhile, particularly if it's going to be costly to remove something that the agency may not own. It can be really helpful to not only determine what the safety impact is going to be, but if it's worthwhile to do it in this case.
Yeah, multifaceted approach. One more question came in. Does the left or right looking intersection sight distance include multi-lane approaches?
Yes. So that was one of the issues that we really tried to get at in this research, that we just couldn't dig any more out of it. So typically, we would like to treat multi-lane and two-lane roads separately, particularly because we do have divided and undivided multi-lane roadways, and we really expected to find a difference with the left-looking ISD when we had the number of lanes there. But because of the amount of data we had, because we were looking at such a targeted crash type, we really couldn't find any nuances within the data that were really telling us. There was no real interaction between the left-looking direction and the number of lanes on the major road approach. And I'm guessing that's because of the interactions we were already finding with traffic volume, which is highly correlated to the number of lanes there. So we would reasonably expect to find a difference for multi-lane and two-lane roads with the left direction, but we didn't find anything with this specific data set.
Interesting.
Because we did ultimately have to develop just kind of one set of models here. We weren't able to look at even just breaking it out and developing different models for multi-lane roadways and different ones for two-lane roadways. It was all kind of lumped together. So that's why I tried to highlight that we included those factors in the model, but then they weren't found to be associated with the impacts of sight distance themselves.
All right. Well, we have nothing else coming in the chat. You kind of answered my question with the general crash modification factor talk. Wanted to say thank you so much for your time putting together the presentation and being with us today. Dennis, do you have any closing remarks? Reminding again everyone that we have a webinar next week, and the recording and the PowerPoint for today's webinar will be posted on the website. You have a link to that location on the email invite.
I just wanted to say, Scott, thank you so much for giving the presentation today, and I hope all the attendees enjoyed it. And as Anthony just mentioned, I look forward to talking or seeing everybody again next Wednesday for our next webinar.
Thank you very much for your time today. I really enjoyed.
All right.
Yeah, thank you. With that, I'll go ahead and end the recording. We'll stay on the line for a few minutes in case anything else comes up. See you next time.